there is another part. This is the magnitude part. Few things you need to remember. The first thing is how are you going to identify the peak over here? Depending on your damping ratio, you're going to identify how tall this one is going to be based on your the equation I just erased over here. You should be able to find out if your damping ratio equals to 0.1, how much dB we're talking about. If it's 0.2, how much we're going to talk about, and those kind of stuff. The other thing that we might need to know is phase. Again, this is second order system. We have two poles. When we have two poles, how many degrees we're talking about over here? From 0 degree to what?
Negative 180.
Negative 180. Okay, and when we are at omega over omega n, the ratio is 1. It is going to be negative 90 degrees. Okay, but another question we have is, will the damping ratio affect the shape of the phase change? The answer is yes. So if we have smaller damping ratio, it means that it will change more sharply. If our damping ratio is large, it is going to change everything slowly, okay? But when we are dealing with first order system, we know there is a start point where the phase starts to change, and there is an end point where my 90 degree is going to be end at that position. Do we have the corresponding things in our second order system phase part? Yes, we do. So it will start at omega 1 and end at omega 2 for individual omega n. This one is going to be 1 over 5 . The second one is going to be 5. If you wanna ask me, how do I get the equation? I don't know. I don't remember. This is just something you just need to remember. So it's 0.2 and this one is 5. So depending on how much damping ratio you have, it's going to change its shape. So you're going to see if your damping ratio is small, it's going to be something like this. But if your damping ratio is large, okay, so look, if you have your notes with you, you should be able to observe the change in the second order body plot listed in the notes. Any questions? So those things are something we need to remember. In the phase part, the most important thing you need to know is those two formulas. So when you remember those two, you should be able to find out what this one is going to be. And if you are dealing with this one, just follow the formula, finding out the peak magnitude, and everything will be fine. Any questions? I'm not going to repeat things in the second order zeros because it's nothing different, just upside down. So I believe you guys can go through this page yourself. So let's deal with one example. So I'll follow the procedure that I was writing down over here to deal with second order Bessel function. So this example is G of S. equals to 2000 s squared plus s plus 25 in the denominator. So what we're trying to do is to identify individual parts, then draw that on a body plot separately, then combine everything all together. Before we can do that, what do we need to do? We need to separate this equation into what? Individual, poles, zeros, and gain. So I know I have 2000 in front of everything. I'll start from the poles. That is s over 1. And I have s plus 200. 200. So when I do 200 over here, what do I need to do? Divided by 200. Then I'll deal with s squared plus 10s plus 2,500. What do I need to put over here?
2,500.
So what do I need to do over here? 2,500. I still have one more to go. S squared plus s plus 25. 25. So I got 25 over here. But before I move on, is this a second order equation, or this is a combination of two first order equations?
Second order.
Why? Because of what?
Damping ratio.
Damping ratio is small. How about that one?
Second order.
That one is also second order. So just be sure you know what's going on over here. Then we will start to prepare everything. I think you guys don't need to draw this. You've got the chart in your note. So when you are preparing this part, please print out several copies of this thing. You will be handy. Otherwise, it's just tedious. So let's get started. So over here, what do I have? 3, 4. Okay, so how many parts will I need to deal with? 1, 2, 3, 4, 5. Based on your understanding, your professor here is very lazy. So I don't want to deal with 5. I just want to deal with 4. So I'll combine those two together. Why? Because if my omega equals to 1, it will become 1.
0.1.
0.1. If it's 1, then it's going to be at 0, but when it's 0.1, it becomes 0 dB. So I can eliminate some part of the equation and make my life a little bit easier. Just a little bit. Better than nothing, right? So I'll collect all the colors. So I'll have magnitude. Nothing fancy, right? This is just what I repeat over here. The only difference is in this equation I get everything as this. In this equation I get every variable becomes j omega. So first thing, this one over here, when at which frequency, this one is going to be 0 dB. 0 dB, which means the ratio is 1. 0.1. I got this one over here. What is a slope? 20 dB or 40 dB?
20 dB.
1 dB. So it's going to be like this. Okay, I'll stop here because that's my lower limit. How about this one? This is what? First order Paul. So it will be at 200, which is somewhere here, in here. So I'll have how many dB? 1 dB. This is too steep. Okay, so this is my 200 over s plus 200. This is 1 over s. Then I have, let's deal with this one first. So this one over here, I got my omega n is equals to 50 radians per second. What is my
0.1.
0.1? Very good. So based on the previous page, I have telling you the peak of resonance at resonance frequency is how much dB, how many dB? When the damping ratio equals 2.1. I think I wrote it down in the previous. Right? It's 14 dB. So when you have your frequency at 50, which is around here, I have around this one 14 dB as the peak. And this one is what? Second order. So what is the slope? What is a rate of a slope?
Minus 40 dB.
Minus 40. So it's going to So what I'm looking at is so far any question? I got this one, and this one taken care of. I still have this one I need to draw, but this one is what? Upside down, because this is a zeros, a pair of zeros. So this one over here, what is my natural frequency? 5. What is the damping ratio? 0.1. So how much dB is the peak?
Minus 40.
Right, so it's going to be around 5. So it's going to be around here. And I got somewhere over here. And I have 40 dB ascending. Any question? I got 1, 2, 3, and 4. All 4 lines together for this one, this one, this one, and this one. And this one. I combine those 2 together. And that is one of the plot. And I have done my magnitude. I need to put my phase together. So let's start on the first one. It is going to be this must be a plus, right? Because this is a 0. How about this one? What is the angle of this one?
Negative 90.
Right, very good. So this is minus 90. And this one we don't know, so it's going to be negative 200 J omega plus 200 minus okay. So of course I'm not asking you to plot everything point by point. We got the tools we have developed in the previous in this class. So we're going to use those skills. So let's start from the first part. So this one is something we need to know, and it is going to be damping ratio equals to 0.1. So I know my natural resonance frequency is going to be 5. So I know it's going to be ascending to 180 degrees, right? But we would need to know what is my omega 1 and what is my omega 2 for the 0 at omega n equals to 5 radians per second. Omega z1 is going to be omega z2 is going to be, understand what I'm talking about? Those two are the formula. 0.1 is because the damping ratio is 0.1. Omega n is 5, which is based on this one. So this part over here is going to give you 4.25 radians per second. This one is going to give you 5.87 radians per second. Which color I was using? I used white. So I have about 4.25 over here, and 5.87, which is around here. So I know at 5, I must have positive 90 degrees. So this one over here is going to be this phase. For the second one over here, 0.1 divided by S or J omega, it is always negative 90 degrees. So this is going to be once more. Do the gain over here going to, well, the gain over here affect the phase? No, because gain does not do anything about the phase. So when it doesn't matter, this is 1 over S, 100 over S, 1000 over S, 1 mega over S. It is always negative 90 degrees. The next one is the first order one. The first order one is going to be 200, somewhere here. This one is a pole. So how many degrees are we talking about? Negative 90. So I know at this point it must be negative 45. When will this slope start?
0.1.
20. Very good, because it's 110. Where is going to end?
2000.
Okay. Okay, I still miss one. Which one? The second order pole. So again, I'm using formula. Zeta is 0.1 because of the formula. Omega n is 50. So clearly, this is 42.5 radians per second. Omega P2 is going to be 5 to the power of 0.1. So it is going to be 58.7 radians per second. So it will be about here. Around here and around here. So I'll have everybody understand what I'm doing over here? The next thing we need to do is to combine everything all together and you'll be done. Let's use glue. So this is 0 all the way, but this one got a slope. So the dominant one over here is going to be this one. And when it starts to hit the first 0, you got about -40 over here. Right? And it will start to ascending. But when this one is ascending, you still under the effect of -20. So the slope is not +40, but it should be what? +20. So the slope is going to be smaller. So be sure you draw that correspondingly. And you will hit your second peak. Now what? You will start to hit -40. Now this is a +20. When you hit -20, it becomes what? -20. But it's just a little bit over here. Then it becomes what? You hit another -20, so it becomes -40 again. So this will be the system response of the overall GJ omega. Is that clear? Everybody understand what I'm doing over here? Though the line looks a little bit crazy, but should be straightforward to understand, right? How about this one? Where should I start everything? Minus 90, right? Because this, all the other three parts are 0 degree. So the only thing we affect the system is the integrator. So I'll start my to here. Then what happened? Start increasing. 2 plus. Right? And it will keep on as flat. But when it becomes 50, this is no longer flat because the slope over here start to take place. So it will be something like this. Then you are going to have this one plus the effect of this one. So it will be a little bit deeper. Then it will be moving toward to here, the -180. And this is going to be the face of the GJ omega plot. Is that clear? Everybody understand what I'm doing? Other than it looks a little bit well, it looks good actually. Very colorful. Is there any part you feel is difficult? Or everybody is taking photos of my drawing? Thank you very much. But when you have this kind of stuff, again, I would ask you guys to use MATLAB to plot everything all by yourself. Okay? Ensure you understand what I'm doing over here. Okay? The only part you might not be positive over here is the transfer function over here. This one, you can just do G equal to TF 125 and 25. That'll be fine. Even though it's improper, but MATLAB can implement this transfer function. So just like what we did earlier, you just separate everything. You just separate this one into 4 individual transfer functions, then plot one by one, and combine everything all together to verify you understand how this figure is synthesized. Okay? That will be important because you need to understand why I get this one, and if you are not so confident what I'm doing over here, it would be a great idea that you just plot everything using MATLAB yourself. Is that clear? So that is pretty much multi-plot. So how are we going to use multi-plot? So over here, this one is a peak value. Normally, when we are dealing with our control system, overshoot, we do not like overshoot. And we do not like to have a resistance because when this one is 40 dB, it actually amplifies more than one time of the amplitude. This one is going to destroy your system easily. So every time when we see there is a peak in your system, we try to eliminate the peak to be input as 1, then output going to be also as 1. So that would be the controller design based on the compensation over here. So when you have something like this, what are you going to do? You are going to design the controller like this. Right place at this position, cancel out the peak, then your system is going to be fine. But we do not want to do pole zero cancellation, in particular when the system is improper or the system is not stable. We do not want to do that. So there are many other tricks or techniques we can use to do the controller design. That is going to be covered in topic 9. Any questions so far? If not, then we're going to talk about a very important thing. Frequency domain analysis.讲这个事情。